So on the other hand, for dependent events A and B, if A depends on B, then the probability of A and B is the probability of B times the probability of A given B. Meanwhile, if B depends on A and B is the probability of A times the probability of B given A, where if you want to just stick to one, you could rearrange what A and B are, but either of these are essentially what we're looking at. So we're going to finish here with an example. So for this example, we have the two cards are selected without replacing the first card from a standard deck of 52. And we want to find the probability of getting a queen on the first and then a king on the second. So we're finally going to clear out that example we've been talking about since we started this section, where hopefully by now we're pretty confident that if we want to talk about this relationship A and B in terms of probabilities, the event B will depend on the occurrence of event A under these assumptions. So in this case, we will have the probability of selecting a queen, which I'll say PQ here. It's event A, as it were. And then we will multiply that by the probability of getting a king, given that we already have a queen. So this takes the role of B given A. Feels very natural to write A and then A given B, but that wouldn't make very much sense now, would it? But in any case, that probability for B is 4 out of 52, as we saw, while king given queen is 4 out of 51, as we also already saw. So in total, we will have 16 over 2652 as our probability written in the form of a fraction, though we could reduce that. Instead, we'll just jump to the decimal, where this is approximately 0.006, so less than 1% chance, which should hint at just how unlikely it is to get certain nice combinations of cards. And next, we're going to look at one more example that has a little bit more setup to it than this one. Here we have that 18,187 U.S. allopathic medical school seniors applied to residency programs and submitted their choices. Of them, 17,057 were matched with residency positions, and about 79.2% got one of their top 3 choices. Medical students rank their programs in order of preference, and program directors in the U.S. rank the students, where you get a match if a student's preference list happens to overlap with a program director's preferences, where you get the student in a position that they want, where they are wanted. Find the probability that a randomly selected senior was matched with a residency position, almost made it, and it was one of the senior's top 3 choices. Well, for this, it's a lot of words, but the truth is the math here is not that complicated. What we have to understand is first a bit of notation, where we're going to let A be the event of a match, and B is that the match was a top choice. So, if we want to talk about the probability of getting a match, that's just the probability of A in this case, which here is the number of matches, 17,057, and that is out of the 18,187 who applied, where from there, the probability of a top choice given the match would be P of B given A in this case, and that is our given percentage of 79.2, which is 0.792 as a decimal. So, if we want the probability of both of these things, A and B, that is, we get a match and a top choice, we have to bear in mind that we're looking at that top choice given that they were a match, because you can't have both without that conditioning, well, it's just going to be the product of the match with the choice given the match. Just, you can't get the match if you didn't apply, and you wouldn't have applied if it wasn't a top choice. But here, and I know it's bad form to write a product of a fraction and a decimal like this, but it still gets us to the right place. That the probability we want here would be about 74.3%, 0.0743. So, it's about a 3 in 4 chance that one of these students will get into the top choice, that one of these students will get into a program that they want.
I got in! I got in! I got into Princeton! Yeah! Yeah!
I'd say that's a pretty good chance, but it's my opinion. Some may say that a quarter is too many opportunities for things to go wrong. But anyway, this is how we look at our cases where we want 2 or more things to happen either at once or in direct sequence. In our next section, which we'll get to next week, we'll be looking at how we can find probabilities where we have one option or another using what's called the addition rule. But that's stuff for 3.3. And for that, I'll see you next week. So have a good one.